want to talk more detail how to generate the pixel, pixel, because SAR image is like the optic sensor image. How to generate, for example, this optic sensor, optic image is from the projector. It's illuminated to this screen, and this image is composed by the pixel. And how to generate this pixel? I want to talk. But in the case of the synthetic aperture, okay, that's the okay, the history of the SAR sensor. I will skip. I've already explained in detail. And the SAR image signal processing history itself is we can define to be two periods. One period use the analog and one period use the digital one. But right now we use the almost fully digital. Digital. But in 1960 they used the first is the holographic technique. Actually, this technique is based on the holography. To make the three dimension. And the process use the many source to generate the three-dimension information. So how to generate the this many source is we use the SAR sensor. When SAR sensor transmit, when SAR sensor moving, then they transmit the pulse. This also transmit the pulse. Then from the response from this pulse, then the come back. Then from this sensor, this source, look like many sources. They transmit, then scattering from the objective. But actually, even we want to observe this object from this, we already can get the response. Then we transmit and we will get the response. And here also same. Get this. So from this 1, 2, 3, 4, it's many source. We want to reconstruct this. So to generate this one pulse, we need the information from it. To generate one, we need many data. Okay. Then, of course, if you want to generate this one, is you need, this. Yes. And here, so like this. Just like below. Okay, and this the shape of this response actually is like this one. And later I want to talk. We use the chirp pulse, and the response of the chirp have the the spectrum. The spectrum you will find the spectrum like this. Yes, and okay, it's very dense. Yes, and you like this. And look like block. Yes. It is the response from this just one object. Then from this block, first from this block you want to make the compression. This direction is range direction. Yes. Range direction. So you need to make compress and to be just one line. Yes. Yes. From this line, then you want to generate just one pixel. I never find a green. To find green. Okay? Yes. You want to generate just one pixel. To generate one pixel, you must merge this one to be one block, one line like this one. Yeah. is range compression. Yeah, range. And then you make this line to be 1 point. Yeah, because this azimuth. Yeah, azimuth. Yeah, very easy to process, but processing is complicated. Okay, yeah. It is use the optical processing method, the optic, yeah, holography. Then in 1970, actually I'm born in 1970. Yeah, you know, in this time they already launched CSAT. Yeah, I just born still, but they already launched CSAT. Yeah. Yeah. And they started partially use the digital processing, yeah, partially, but it still mean analog. Yeah. And then 80 is even in CC mission, they change to also gradually change to the digital processing. Yeah. And from 1990s is the optical processing, the analog one, yeah, is completely digital. Yeah. And they use you know, in digital one. But Almax, it is the mission of the Soviet Union. They use the hybrid processor, optical and the digital one. Yeah. But right now in 2000s, yeah, in the 2000 era, all is completely digital one. Yeah. Digital. Yeah. Okay. And now I want to talk is not analog. Yeah. I want to talk in digital. Yeah. Okay. Digital processing algorithm. Yeah. You can find this response. Yeah. You know, this response is like this one. Evident one. Yeah. But this is the opposite one. Yeah. Like this one. Yeah. So this block you will generate to be just one pixel. So this last, yeah, the length of between to this area to this area, it depends what depends to what? Yeah. Because it depends on the beam width, yeah, the beam width of your antenna. Yeah. For example, here's PO, is maximum, yeah, and here the PO divided by 2 or minus 3 dB. Yeah. So this width, yeah, this width will you will find, okay, the block is like actually, if you use your antenna, okay, antenna large, your beam is small. But if your antenna small, your beam is large. Opposite, please remember. Okay. So, if you find like this one, you can predict, oh, the satellite use the antenna width is how many meter. You can predict. Yeah, yeah. From this prediction, you can also predict the height of the satellite. Yeah. Even the spy satellite, if we know the knowledge of the synthetic aperture radar, you can say, oh, the specification of this satellite is blah blah blah. Yeah. Yeah. Okay. Then after we process it, will be like this. Okay. This raw data, then range compression, azimuth compression, and you can get this. Yeah. Like this one. Yeah. It is the azimuth. Yeah. And you can find the block like this one. It is the response from 1 point. Yeah. 1 point. Yeah. And you make the range compression to be line. Yeah. And then from this range compression, after azimuth compression, yeah, azimuth compression to be 1 point. Yeah. So you want to generate this 1 point. Then if you want to generate this point here, you can use also the block. Yeah? The block is the next one. Yeah? That's the shifting process. And the third digital processing is I can classify. First is using the spectrum analysis method or dynamic methods. Then correlation technique. correlation technique is means the scattering wave you receive, then you compare with your what kind of pulse you transmit it. Yeah? Then with correlation, compare. Yeah? Compare. In frequency domain or time domain. Yeah? Okay, now I want to talk in time domain. In time domain, you can find two-dimension algorithm or range Doppler algorithm, and I think also many omega k, yes, algorithm, yes, or job scaling technique, and I think many. And I want to talk. It is the easier one. It's range Doppler algorithm. This technique is used in many processes. Yeah. Okay, please remember RDA is RDA, range Doppler algorithm. RDA. Okay, before I start to explain how to process or the processor of the synthetic aperture radar, I want to explain the geometry of the SAR sensor. First, this direction called the platform direction. Okay? It is satellite, aircraft, or UAV. Or you will bring yourself. You can fly and you get this. This is the platform direction. Okay? Sensor and antenna we put here. Then here is nadir. Yes? Nadir. And this direction parallel to this one is we call in the azimuth direction. Please remember, azimuth direction. Yeah? And then perpendicular to this direction we call as the range direction. Yeah? Range direction. Okay? Azimuth and range. Yeah? Here, range, azimuth. Yeah? Range and azimuth. Yeah? Okay? Then from antenna to the object, it is also important. We call as the slant range direction. Yeah? The real direction is a slant range from the satellite of the sensor to the object. Yeah? We call a slant range direction. And then here, this angle, yeah, from the sensor to the object, and this angle we call as the off-nadir angle or look angle. Look angle or off-nadir angle. You can find in the spec of the satellite. Yeah? Off-nadir angle is how many degrees, or look angle is how many degrees. Yeah? It means depend on the mission. Yeah? If you want to observe the ocean, I think better close to the 20 degrees. Yeah? It's very close. Yeah? Because the ocean head is maybe maximum is 30 meters. Yeah? Yeah? So I think unit is very close. Yeah? You know, it is the platform direction. Then you put here the nadir, yes, 20, yeah, 20 degrees. If you want to monitor a tsunami, yeah, it is better, yeah, 20 degrees. But if you want to monitor the forest, yeah, forest, it is on the mountain. I think you cannot use it. It's very close, yeah, yeah. You need more, you know, higher, yeah, 38 or 45 yeah, degree, yeah, okay. Yeah.
Or look angle.
Look angle, because you want to discriminate is a big object, yeah, big object. Yeah. So you need range, more high range, or long range. But it's close range, you know, in the head is small. It's better use the look like the altimeter, yeah, altimeter. Yeah. If you want to the head some object is use the close to the nadir is better. Yeah. Okay, and then if you talk in military, I think depression angle here is more important. Yeah. It is from the aircraft, in the point of view of the aircraft. But in our case, for the civilian application, it is commonly we talk in use the look angle or the off-nadir angle. Okay, and then this angle is incident angle. If we use for the UAV, incident angle and off-nadir angle is almost same. But if for the satellite, it's different, yeah, because it's very high, yeah, very high. the height is, for example, 600 kilometer, 600 kilometer, and we must consider from the center of our Earth. Yeah? So the incident angle and the look angle is different. For example, our Earth. This angle, yeah, incident angle, and this look angle is different. Yeah? But if UAV, yeah, UAV here and here same, yeah, it is UAV. It is sun. Yeah. So when you design the sensor for UAV or for your satellite, yeah. But if your UAV is 100 kilometers, so it is maybe different. Yeah. 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 Okay. And next, okay, our antenna have a beam width, yeah, the beam width. Yeah. For example, we translate like this. Okay. And the beam width like this one. Okay. And here's PO, and here's the minus 3 dB, yeah, or PO half. When we define the beam width, yeah, the beam width is the power when half. Yeah, the power half. For example, here's the peak power, and here's half. Yeah, then half power. Yeah, half power minus 3 dB. Yeah. If you heard minus 3 dB, oh, it is half. Yeah, half power or half dB. Yeah. Okay. But you cannot talk. I don't know. In Christian, is your half of my body. Yeah? Your is minus 3 dB of me. Yes, just you. Okay, like this one. Yeah? You connect this point to this point. Yeah? This point we call as the near field. Yeah? And this point is far field. Yeah? Okay? Yeah? Far field. Near field. Yeah? Yes, sir. Yeah? Here the near field and here far field. Yeah? This area we call as the sweat. Sweat width. The sweat width. This area. Sweat. Sweat. And this point is our target, and from this point to nadir to this point we call it the ground length. The ground. Okay. Then we use this some term in my explanation. Just remember here, if the antenna is large, the beam is small. But if the antenna here small, the width is small, so the beam width is large. Yeah? Yeah. So if the shape is antenna like this one, so the beam is like this one. You can see in the iPod, yeah? In the iPod, the shape is like this one. Yeah? Why? Yeah? Because you can we want to see. Yeah? For example, here the iPod. Yeah? So then the shape is like this. Yeah? It means we want to observe the area like this. Then we moving, okay? Moving like this one, and you can find it. Yeah. With the beam. So if the airplane here, so why the shape is like this? It is because we want to what is the monitor? Yeah. With this block. Yeah. Then maybe one minute, around 1 minute, maybe just 1 minute 20 times, or yeah, we can set the number of the pulse. Okay, like this one. Yeah, we transmit like that. Yeah. It is one pulse. Yeah, one pulse transmit, but in 1 second maybe 100 pulse. Then we can detect every second is at least is 100 point we can visit. So we can predict the speed of the aircraft and the position of the aircraft. Okay? So then it is the width of the pulse. Yeah, we transmit for you. Yeah. Thank you. Okay. Next. Half value. I'm already explained about the half value. Yeah, it's minus 3 dB. Yeah, minus 3 dB. To derive the beamwidth of our synthetic aperture. For example, JERS1. JERS1 is have the length of the antenna is around 12 meter. You know 12 meter is maybe twice of this room. Yeah, the antenna. How to bring the big antenna to the binocular? Yeah. It is big. Yeah. It's also a big problem. Yeah. And then the width is 2.2 meter. Yeah. 2.2 meter. So then from this parameter you can derive the half value of the beamwidth. Yeah. By using lambda divided by this value. For example, alpha is divided by b. Yeah, this one. So this beamwidth is around 5.3 degree. Yeah. Then this line, in this line, if long, so the beamwidth is small. Yeah. So you can find 1 degree, even 1 degree, but from 700 kilometer. Yeah. 1 degree is maybe around 14 kilometer. What is the meaning? 14 kilometer. So this width, yeah, it is 14 kilometer. Yeah. From here to here. Okay. You need 14 kilometer to generate 1 pixel. Okay. The response point of 14 kilometer. Okay. And it is the azimuth. Yeah. So it is the azimuth, and here the range. Range is 17 kilometer. It means your sweat width, yeah, the sweat width, this one, 75 kilometer. 75 kilometer. Like this one, yeah. This beamwidth, this beamwidth is 14 kilometer. And here, this direction, the range direction is 75 kilometers. So you can find on the spec brochure of the JERS1, the sweat width is 75 kilometers. Okay. Okay, this is the antenna, and this is the real antenna. Yeah? If here's large, you can find the beam is small. But here, small, the beam is flat. Yeah. So here is small, so the beam is flat. Yeah? Flat here. But here, small, so the beam here, in this direction, is small. Yeah? Okay, we also developed by ourselves some antenna. Okay? If you have time, so you can visit my facility, how to design and how to manufacture and how to measure the antenna inside our anechoic chamber. And yes, we plan to install our antenna inside the UAV. We also develop UAV by ourselves. And here, it is microsatellite. It is the Tokyo University microsatellite. measured in our anechoic chamber, in the underground of our laboratory. You can see our facility. Yes. Okay. Next, it is the real, footprint of our satellite. Depend on the antenna shape. So here beam is 14 kilometers, but here 75 kilometers. Yes, 75, and here 14. Yes. To generate one pixel, we need 14 kilometers. Then I've already explained. Yeah. Okay. If we want to observe this point when moving like this one, okay, you will get the footprint like this. Okay, it is the response from just one point, but actually we have the beam spreading of the pulse. So we'll find the block. Okay, when we design our satellite, we need, radar equation. It is the simple one. The simple one. We want to input the power. Then, if we input the PT and how many power we will receive. Yes? So we will receive this. So we must calculate. And if the effective surface of the receiver antenna, then G is the gain of our antenna. It's very important. If you want to reduce your if you want to reduce the power of your antenna, I think better you increase the gain. Yeah? The gain is sensitivity of your antenna. Yeah? If your antenna sensitive, you don't need high power. Yeah? But if your antenna is not sensitive, you need a power very big. Yeah? It is same with human. Yeah? If you are not sensitive, you need much money to find job. Yeah? Yeah? But if you are sensitive, you don't need money. Yeah? As many people will come and hide you. Yeah? It is same. Yeah? So you must sensitive. You must increase our gain. Yeah? Or relation with many people. It is same. Yeah? And it is radar cross section or back scattering surface. Yeah? Yeah. Even the object is like this one, but the scattering surface is just this area. It's not the back one. Yeah? So you find object and the scattering, for example, coming and scattering is this area. It's not this one. Yeah? Okay. It is the radar cross section. Yeah? Then okay, let's calculate here. You can see, or I will explain here. First, when we transmit the power PT, then from your antenna will spread to any direction. It look like a ball. Look like ball. So in this case, is when moving with the distance r, your wave will drop. Dropping. Because from the ball, like ball, will spread to it is for example r. And this ball is from if r increase, your power will drop gradually. Okay, but you must consider the antenna. Antenna have the gain. Yeah? For example, the gain is just to this direction. Yeah? just direction. This means it is the gain. Again. So if took this direction, you know, the wave to here is 0. Here is 0. Here is also 0, but here, okay, and here also this gain. Here this gain. So you must consider where you observe. When you observe from here, you observe from here, the gain is there.
High.
So you can find the gain is high, but here is a little bit low, and here lower, and here Z. Yeah? Because the total gain is 1. Yeah? Totally gain is 1. Ratio, in ratio. Yeah? But if you don't consider the antenna, you know, you just consider just a point source, so the totally is, you know, is totally is 1 to any direction. Okay? Then you time it again where you observe. Okay, next this wave will touch this object. This object have the radar cross section is sigma. Yeah? Sigma. So you time it with the sigma. If the radar cross section is big, you will find this total is big. But if radar cross section is small, you will find the scattering of the small. Yeah. From this object is if is big is the scattering also big. But it's small, this object is small, I think the scattering also small. It is the meaning of this radar cross section. Yeah. Okay, and then after that is scattering again. Yeah, to any direction. Yeah. This one. To any direction. So it is, for example, R is also same. Yeah. So you can times R. Because spreading. Yeah. Spreading. If R is large, yeah, so this power will drop. Okay, you know, I want to explain as simple as possible. Yeah. Because from this object, the wave will, you know, spreading again. But you know, this from this object is scattering from this surface. Yeah? It's not from this surface. So this case in the real condition is spreading like this. Yeah? Yeah. Yes, almost there. Yeah? Almost. Okay. Yeah? Okay. So we consider the scattering from this object with this object surface is sigma. Yeah? The phase. Sigma. So y time sigma. Then from here spreading again, it look like gain. Yeah? Look like gain of this from this to this sigma. Then okay, after that we want to observe by using our antenna, where our antenna the effective surface is A. Okay? Just A. So you find with A. It means if your antenna big, you will receive big power. But if your antenna small, you will receive a small power. Small power. Okay, it is, you know, you finish and you will receive. It is the total of the receiver. Yeah? The total receiver. So you can get this one. It is the basic one. You not yet include your frequency, yes, yeah, and other, you know, parameter. Okay, I will explain. It is the real when you want to design your sensor. Yeah, you want to design depend on the, for example, you will design depend on the sweat rate. Okay? If I want to observe, for example, 60 kilometer. Okay, we set here. Then what frequency you want to use? So you can insert here. Then later, if sweat rate you already designed and the height, how many kilometer? if the head, then you can calculate the half power is some degree. Then you can design your we need the antenna width is a millimeter. Okay. Then if your antenna width is also fixed, you can define the PRF, pulse repetition frequency. How many pulse you need to transmit? Yeah, because it depends. If your transmitter is not enough the PRF, you cannot generate your image. Yeah. Yeah. If your antenna small, means you must transmit many. Yeah. You must increase the PRF. But if your antenna big, yes, you can reduce your PRF. It look like what is fishnet. Yeah? Fishnet. If you use a big fishnet, yeah, you can, you know, and you can find many fish. Yeah? But if your net is small, you know, probably you must, you know,
a lot of time.
Yeah, many times.
Many times.
It is same. Yeah. If you use a big antenna, is the best one. But we have a problem. If big antenna is very big, and if we launch, you know, spend much money. Yeah? So we need to design the efficient one on the optimum size of your antenna. And then, okay, and here antenna elevation. Also the antenna elevation you can elevation width, yeah, on the elevation size you can also design. So in this case is which parameter you want to design the first time, yeah, depend on your vision. Okay, and then later you can also calculate the power on the antenna gain and the observation, and finally the SN. SN is how many dB? For example, 25 dB. I think the common day noise 30 dB. Yeah, 30 dB from 0 to minus 30 dB. Yeah, to make the range of the observation. Yeah. For example, 15 dB is the response from the forest, and minus 20 dB is from the soil. Okay. And you can make you know, the classification. But here is also, you know, depend on the scattering. Yeah? On the scattering is SN will have a relation with your low noise amplifier. Yeah? If low noise amplifier with wide range, I think the price is very expensive. Yeah? It depends. If we develop in university, I think it's not so many money. Yeah? So I think, you know, we will find, you know, it's not so good. Yeah? But enough for university. But if you want to get the picture and you want to sell, I think better you need, you know, a good performance of the low noise amplifier. Okay, it is when you want to design the procedure. Yeah? And for the detail, you can ask me. I can explain about how to the real calculation. Okay, the pulse radar. It is from our antenna, and for example, you want to observe this tree, house, and the concrete building. We transmit, you know, it is the time. For example, 1, 2, 3, and 9 seconds. We'll touch this tree and we're scattering, yeah? Scattering and back and receive in at 18 seconds. Yeah? We transmit is high power but receive small. It depends on the object. Sometimes small, higher and higher. It depends on the object. If the response from the metal, I think is very high. But the response from the tree is low. Yeah? Because it's partly a short by the tree. Yeah? Then, okay, this is the scattering wave, and here the transmitted pulse. Yeah? It means here we can use as the reference function. Reference function, and here is the scattering function. Yeah? Then later we use the cross correlation. Yeah? Cross correlation, and we can find the response from each object. Okay, to observe this area, we need time, yes, transmit and receive. It means if this one is Rn, yes, Rn, this 2Rn, because transmit and receive, double, yeah, double divided by the velocity, yeah, the wave velocity, 3 times 10 power by 8. Yeah. And then far field is 2Rf divided by C plus tau, yes, plus tau, yeah. Tau is the to cover this area. We need plus some tau, yeah. Or yeah, also it depends on what kind of you want to define. And the continued time on the receive pulse is just this one, yeah, this one minus this one, yeah. And you can find the observation time, yeah, observation time. Okay, and here the pulse power, including the transmitted power, is peak power times the pulse width, the base width, yeah, pulse width and the power, yeah, like this one. So I think if you define the power, the time transmitted power is larger, you need, the power is large. It's possible is you must calculate to find the optimum pulse width before you launch your satellite. Okay. Because if not, your satellite is inefficient, inefficient. Because to get the power on the space is very hard. Okay. Actually, when we transmit in the spaceborne, yeah, we transmit and suddenly it's not come. Yeah, we need maybe some second. Yeah, some second. Wait and okay, finally come. Yeah. But if UAV is very close. Yes, even you not yet finished to transmit, it's already come. Yeah. So you must calculate. Yeah, when transmit and when transmit. Yeah. So if not, it's collision. Yeah, collision.
Collision.
Yeah. Okay. And here, when you want to monitor one, just one area, yeah, one area. So in this case is the echo. Then you need to resample. Yeah, resample. For example, the response from this area. Then you can when you get the pulse, then you resampling. Yeah. Resampling, then this is the resampling from pulse 1. Then you say, then like this. When you want to monitor. Yeah. From this area. Okay, this is the response from pulse bar. Your aircraft is moving. You transmit, yeah. Then the pulse scattering from this area. This is then you set. And next, the response from this line. You will save this response. And next, the response from this one. Then you save. Then this number 1, number 2, then number 3, and then you save, and you can find this raw data. You can save this one as raw data. After that, then we process by saying this processor. Okay. It is the response from just one pulse, from the one pulse. Okay, I'm already explained to you. Yeah? We transmit and receive the sound. It is the receive from one pulse. Yeah? But we receive together. It is the response and receive by using left-handed and right-handed. In this case. Yeah? And okay, right. Here's the real one. Yeah? Transmit and receive. The receiver is complex. It's very complex. It depends on the object. Yeah? And when we process, first is we receive the raw data. Okay? Raw data is from this one. Okay? From this one, then we use the range reference function. Range reference function is we use this one. Okay? What kind of pulse we transmit? Okay? But we can also simulate the real pulse. Okay? Then we use as the reference function. If we know the parameter of our radar. Yeah? I think we know, we transmit, for example, with the bandwidth at 50 megahertz. Don't forget, yeah? If you design your system, don't forget that your system. Yeah? Because if you forget, so you cannot regenerate your image. Yeah? Okay, so you must save this pulse. Okay? And then we process to the FFT. Why we change to the frequency domain, from time domain to frequency domain? Because later I want to explain that if we use in time domain, you know, cross correlation is consume time and consume the memory. Yeah? So if we save to the frequency domain, we can just select all the component of the scattering wave at frequency, center frequency, and the transmitted pulse on the reference function and the scattering one in the same frequency. Then just multiple. Yeah. If not, in the time domain, you need to cross correlation is times, then summation, time summation, or take the total and it's consume time. Yeah. If in frequency domain, you just one time to multiple. It's not so consume time. Okay, then here's the range FFT, and then here multiple. Then after that is you change again IFFT, yes, IFFT, and then corner term, just corner term to to make the process is if you change the direction of the FFT. Yeah. We need to make the corner term, then azimuth FFT. After the range compression, here the azimuth compression. Yeah. Then it is here also same azimuth reference function, then FFT. Here the range reference function. Yeah. You must derive the range reference function and azimuth reference function. Yeah. In the next slide, I think I want to explain how to generate. Okay. Then after FFT, you know, we multiple here, then IFFT, and you can get the SAR image. It is the process in RDA, ring Doppler frequency. Okay? Ring Doppler algorithm.
Range Doppler and Doppler center is not the same.
Okay, later, yeah. I thought here is used in the center frequency, but actually later, because the effect of the velocity of our Earth, or if you want to launch to a different planet, you must consider the velocity of the planet. Yeah? So in this case, then the relative frequency. Yeah, you must consider the relative frequency. So in this case, is the frequency of Doppler is the center plus some delta L. Yeah, plus minus. Yes, plus minus. It is depend on when the satellite is ascending or descending, because the Earth velocity, Earth velocity like this one. So the direction of the relative velocity is different. Okay? Plus minus delta FB. This is the final frequency. Okay? When you want to use to multiple here, it is the frequency of the after the effect of the Doppler frequency. Okay? It is okay. Raw data, ring compression, azimuth compression, and minor. Okay? You can get this image. And okay, range compression. Here's before the range compression. Yeah? if we want to split or to discriminate or to know the minimum, minimum resolution. When we don't use the chart pulse, we use the common pulse. It is the time, and here the transmitted signal, and here the scattering. First is when we use the pulse with the width is c tau, and the distance between object A and B is c tau divided by 2. Then, okay, let's the pulse is moving to this direction. Then touch the object A. Then the scattering from object A. Okay, and here this pulse moving this this line, and the scattering is to be like it is almost same. Then here after moving after moving this width, and it's starting to touch object B, and your response here is not clear here. Yes, started to scattering. And after moving, and this one, partly, this length is same, because illuminate the object A. Then illuminated the object B with the width in this one is almost same, the scattering. Then the most important here, after the first illuminated object A, this one, the scattering is same, and illuminated object B, this one, and here same. But you can see here, it's starting to overlap. The scattering between scattering from A and B. So after that, if this object A and B is closer or less than c tau divided by 2, so this pulse will overlap. So you cannot discriminate. Oh, this response is from A or from B. So if you use this technique in the conventional one, so you can discriminate the scattering from A and B. It is just the half of the pulse. So in this case of this technique, if you want to increase the resolution or the distance or to discriminate between object A and B, so you need to make the pulse is more small, more small. If you make this one is more smaller, you can discriminate A and B. But the problem is electronically it is sometimes impossible. It's very short, but you need high power. High power. It's very almost impossible. So in this case is we need some another technique. And the resolution itself. For example, just one cell. If the tau, is 35 microseconds. So if you insert and you want to find the resolution, c tau by divided by 2, and you can insert c is 3 times 10 power by 8, and tau is this one, and you can insert here as the resolution in range direction is 5 kilometer. 5 kilometer. You want to buy the data with the resolution 5 kilometer? What kind of application you want to use? I think possible. It is still in slant rate. Slant rate. Let's consider in azimuth. Sorry, in the ground. In the ground. Slant rate, but in the real ground, how many meter? You can divide. I already explained that delta F divided by sine theta. This is the incident angle, and you can find 9 kilometer. The real resolution is 9 kilometer. If you use this the conventional technique. with the the pulse width is 35 microseconds. Okay. It is one of the illustration. Yeah. If you want to discriminate this A and B, yeah, with the bit the distance is D, so you need this pulse is is very thin. Yeah. So you can discriminate the response from A and B. Yeah. But if your pulse is 1, yeah, 1 is the response from A, B, and offline. Yeah. So you cannot this from A or offline. Yeah. Yeah. This is I think very easy. Okay. To increase the pulse is we can make the pulse is small, okay? But it's almost impossible, yeah, because to to reduce the weight but increase the power. Okay? It is almost because the SN, yeah, signal to noise ratio is to be higher back to be bad. Yeah? And then one of the technique is we use the chirp compression. Yeah? Use the chirp pulse. Yeah? Then let's compare. It is the conventional one. Yeah? And here the chirp pulse. Then the bandwidth of the we use the sinusoid wave and rectangular wave. Yeah? And here the bandwidth is equal to 1 divided by tau. Yeah? And then resolution itself is delta R equal to C tau divided by 2. Yeah? I'm already explained. And this equal to, because beta, yeah? Beta is 1 divided by tau. Yeah? And just tau. Tau you can insert here and you can find it. C divided by 2D. Yeah? Okay. If conventional one, the bandwidth, bandwidth is small. Small. So if bandwidth is small, it is to be, is large. Yeah? Divided by small is large. Yeah? To be large. The resolution large is not good. Yeah? Not good. Then if we use the chirp pulse, you can compare here. B equal to 1 divided by tau, and here is equal to delta F, because in chirp pulse we have the bandwidth. The bandwidth is large. Yeah? So in this case, the resolution is until here is almost same and here is almost same, but B we change to be delta F. Yeah? We can control delta F. If you want to decrease this one or make the resolution is small, it ought to be better. Yeah? So you can change by increasing this bandwidth. Yeah? You can set the bandwidth is to be large, and because divided by the bandwidth, so this delta R on the resolution is to be small. Yeah? Small. It ought to be good. To be good. But in the real development, we must consider the ITU, okay? International Telecommunication Union. They already decided that for the Earth observation in L band is how many megahertz, and in C band or X band is how many megahertz. Yeah? Please, you must refer. Okay? In the case of L band, is 50 megahertz. From 50 megahertz. Okay, it is the chirp pulse. Yeah? When it is the frequency and here the time. Yeah? Within tau on the time, yes, tau equal to 1 divided by delta F. The frequency moving 15 megahertz. Yeah? In this case of the jazz one side, yeah? They setting 15 megahertz. It's very short, 15 megahertz. Then, okay, the frequency itself is F equal to the FO, the center, yeah, center is 1.275 gigahertz plus alpha tau, yeah, and the output wave is to be like this one. I'm already explained to you. Okay, it is the reference function, yes, in range direction. Yeah, please remember, yeah, reference function, yeah, reference function. Yeah. exponential 2 pi j or I, yes, f tau. Okay? It is this function. Then f0 center frequency is 1.275 gigahertz. Then delta f itself is 50 megahertz, and f itself is from this frequency to this frequency, moving, yeah, within 35 microseconds. Yeah. Then bandwidth after detected is B equal to delta f. Yeah, delta f. Then let's calculate. If we compare with the cross correlation, yeah, when we want to observe ABC, yeah, sometimes if the bandwidth, the pulse width, yeah, the pulse width is larger compared to the distance between object A, B, or C. Yeah. Let's consider. But here, if we use the short pulse, yeah, then here, for example, the response from our platform, we transmit and we get the response from A, B, C, and mix, yeah, F mix. Yeah. Then we use this transmitted pulse here as the reference function. Then we put here, then multiply and calculate the total. Yeah. Use this one, this equation. Yeah, reference wave GS and receive wave GR. Yes, here we use the correlation function. Then we moving here, calculate, yeah, calculate, then make the total. If yes 0, and you will find 0. Yeah. But if you move here and here's 0, but here you can find the response from this part. Yeah. Then the total is maybe small. Yeah. But when this reference function and the response from the A is matched, yeah, if matched, so you will find the response is high. Yeah, high. Then also same, when you move and you will get the matched response between the reference function and the response from B. You will get the response is high. Yeah. And then later you can check that from A, B, C, is very close. Yeah. It's very close. But you can discriminate, the response from A, from B, from C. Yeah. So this distance is, you can define as the resolution. Or the resolution itself is in the mathematical calculation is it is 1 divided by delta f. Okay? The real resolution. If we use the chart pulse, yeah, then in this case it's in time domain. In time domain, why we need to move to the frequency domain? Because when we move, calculate, then take the total, and you can find it. And then moving, and this total time is is consumed much time. Okay? So then I think better we calculate in frequency domain. Okay, it is our block of our system. When we want to calculate it. Okay, yes, the chart part. Yeah, the chart part. So here in the transmitted wave, and here the received wave. Yeah. And then here the reference function. The reference function. Yeah. The cross correlation, yeah, between GS and GR, you can find it. Yeah. It is same in time domain. Yeah. And then we calculate, compare last calculation. We thought use the chart pulse. We got that the ground resolution is 9 kilometers. Yeah. And we use a chart pulse. Yeah. Pulse width is 1 divided by delta f, and delta f we already know. Yeah? It's 15 megahertz. You insert there, you can find. Then slant range resolution. Yeah. See tau MC. Yeah, this one. Divide by 2, and you can get just put here, and you can find 10 meter. Yeah. 10 meter slant range. And compared to without they use the chirpers is 5 kilometer. You select this one. 10 meter or 5 kilometer? I think 10 meter, yeah, 10 meter. And if we calculate on the ground resolution, divided by the, certified, and you will find the real resolution on the ground is around 18, yeah? 18 meter. Yeah. So you will find the product of the just one is 18 meter. Yeah? 18 meter. And the product is the spacing is 18 meter. Okay, but this technique is still consume time, yeah, and memory. So we need to calculate in the frequency domain. Yeah? Let's use the FFT. If we use the time domain, this cross correlation, you can explain like this. Why? It is consume time because you know this. Chiba. Plus tau. It is equal to, GR delta T maybe N, yeah? NGS N delta T. Depend on the grading, yeah? The grading of your time. It is n, for example, 1 to infinity. Of course, you can select maybe just 300, 400, but you must calculate every 400 or 300, yeah, to find just one value. Yeah, yeah. It takes consume time. Yeah, and you must, little bit moving. Calculate and get the machine, okay? Or the total value. Okay? So I think it consumes time, okay? Because the integral is we can express by using the summation. Okay? Summation is consume time and memory. Okay? And then I think it's better we transform to FFT and we just get in frequency domain. Just like one frequency, the component in one frequency, and just multiple. Yeah. Compared to integral, I think multiple is more easier. Yeah. So here is maybe elementary school grade is enough. Yeah. But here is university. Yeah. 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 It's easy. Yeah. More easy. Okay. There's more small. Yeah. More small. Okay, next. Okay, until just you have some question? Yeah? Before I continue for the azimuth compression. Almost 5. Yes. Okay, maybe 4. Okay. I'll continue. I still have many slides. Yes. Okay. This is for the azimuth compression. Range compression first, then azimuth compression. It is the final one. Okay. Now let's consider without the azimuth compression. Yeah. If your antenna width, yes, is L, and from the antenna to the object is, the radius is R. Yeah? R. So, and the beam width, yeah, I'm already explained, yes, when we talk the antenna, yes, the beam width equal to the lambda divided by the antenna width. Yeah. If your antenna width is flat, so this is to be small. Yeah, it's same, and then R, yeah, and then R. Yeah. If you see this one, here is, your eyes is, is very, you cannot see it here. Yeah. And you cannot see here. Yeah. So in this case, your focus is here. Yeah. But if you see over there, use very low. Yeah. It's same with the antenna. Yeah. If you observe object is far away, so you know it's very large. It's same if you see in the sky, you will find the universe. Yeah. It's very large. Yeah. It is same. Even just 1 degree. Yeah. From the 700 is you can see 14 kilometer. Yeah? And if you see the universe is maybe how many, you know, how many million kilometer. Yeah? Even just one degree. Yeah? It is same. Yeah. So R, yeah, you can calculate. Yeah. This resolution. This resolution is beta. Yeah. Beta, the beamwidth, time beta R. If R large, the beamwidth will large. Yeah? Then on the coverage, on the resolution, ground resolution is large. But if the B, yes, the B large, also the coverage is large. Yeah? But the beam is small, the coverage also small. Yeah? It is just how to express this equation, or the meaning of this equation. Then let's insert beta. Beta is equal to this one, lambda divided by L. And you can insert here and you can find here. Lambda, the wavelength, time the R, this one, and the antenna width. Yeah? Antenna width. All is depend on your antenna width. Yeah? Antenna width. Okay? Then, okay, let's insert the parameter of just one. And you can insert here and you can find 13 kilometer resolution. Yeah? 13 kilometer is very large. Yeah? Very large. Yeah? Within 13 kilometer, maybe many horses, yeah? Inside in 1 pixel. Yeah? Yeah? So it is the coverage. I'm already explained. Yeah? The coverage is around 13.4 kilometer to cover just one. Simultaneously pulse. Yeah? It's 13.4 kilometer. So I think yes, no application. Yeah? Application. Okay. And next, if we use the Doppler effect, how to increase the resolution? Yeah? Next, we use the short pulse. Yeah? Okay, the short pulse itself is delta F, yeah? The bandwidth, yeah? Bandwidth is equal to 2 FD. Yeah? It is 15 megahertz, yeah? 15 megahertz. This one. And let's we consider if the antenna length is L and the synthetic aperture length is LS. How about the synthetic aperture? If we use just one antenna, you know, the resolution is 13.4 kilometer. But now let's consider if we use, you know, if we move our satellite. Yeah? Later, the answer is this: if we move 13.4 kilometer, you can get the resolution is half of your antenna. If your antenna 12 meter,
6.
or 12 meter, you can find resolution is 6 meters. How to generate 6 meter? You must move your antenna is 13.4 kilometers. Okay. But to get the constant one is you must transmit pulse constantly, and the beam is must constant. Yeah? You cannot. Yeah? Okay. And okay, let's consider when we want to observe this object P. Yeah? When the satellite is approaching to this point and beginning to observe point P. Yeah? Then okay, this is the beginning. Then after that is continuously, yes, observe. Yeah? Then here perpendicular. Then here after that is want to leave. Yeah? Leave this point. Then after that, when satellite in this position, they will final observation to this point. Yeah? After that, leave. Yeah? Okay, this length we call in the synthetic aperture length, or like we put as LS. Yeah? This LS is equal to this illumination width of the real aperture. Yeah? Almost same. This width and this width is almost same. Yeah? So it means the beam width is almost same with the synthetic aperture length. Yeah? So if you want to make the illumination is smaller, yeah, you will find this one is small. Yeah, small. But if it means if you want to observe shortly, I think better you use this big antenna. Yeah? But if you want to observe is in long time, you just need small antennas because the beam is large. Okay. Okay. Then we can derive that the velocity, yeah, relative velocity in this point is Vd, yeah, Vd equal to V, yeah, speed of the satellite, V sin beta divided by 2. Yeah, it is because beta here is just 1 degree. Yeah, in this case it's just 1 degree, so it's half degree. Sin of half degree is almost half. Yeah? Almost half. So you can insert here. Then you can find that V beta is, yeah, it is just approach. Okay? Approximation. Then here the relative velocity, because perpendicular is almost 0. And then when leave here to be minus. Please don't forget, yes, minus. It means it looks like when you drive a car or a bicycle, when you're approaching the ambulance, yeah? Ambulance car, yeah? When you heard the siren, yeah? Siren, when you're approaching, is the frequency will high. Then when in the same place, yeah, it is almost the highest one. Yeah? Then after that it will drop. Yeah? Will drop. It is same. From plus, then drop, minus. Yeah? It is relatively same. Yeah? Okay, next is we want to derive the Doppler frequency from 1. Yeah? This equation, and here beta equal beta equal the lambda divided by L. It is the beamwidth. Yeah? The beamwidth definition. And from the definition of the Doppler frequency, yeah? Doppler frequency equal to 2 Vd, yeah? The relative velocity divided by the lambda, yeah? By lambda. Then you can find, you can consider here Vd is equal to this one. Then you can just insert Vd here, and you can find Fd equal to Bl. Yeah? Okay. Then Doppler modulation change is here, from here. Delta F equal to 2 Fd equal to, Fd is this one. Yeah. You can just insert Fd is here, and you can find it. Okay. Then the effective pulse width tau at the azimuth direction equal to 1 divided by delta F. Delta F, and you can insert here, and you can find this one. Yeah, this one. You can insert here, and you can here, and you can find here by inserting to Fd here, and you can find it. So tau equal to L divided by 2 feet. Yeah. Then okay, this resolution, the resolution itself is equal V time with the tau. Okay, this tau, and you can insert here. And you can find L divided by 2. It's very simple. Yeah? So, when you want to derive the resolution at the azimuth direction, it depends on your antenna size. It's not to the frequency. Okay. If your antenna is 12 meter, so like just one, so you will find the resolution at the azimuth direction is half, 6 meter. 6. Okay, it is also another what is how to prove that finally is the resolution is L divided by 2. It is also simple. You can just see from this derivation. It is more simple. Okay? And then azimuth compression. About the reference function of the azimuth compression. Okay? When the spacecraft moving from this point to this point and this point with the position, yes, x equal to phi t. Yeah? Phi is velocity and t is the time. Yeah? The time. Yeah? And here in the perpendicular distance is RO. Then this distance is R. Let's consider that the phase, yes, the phase change is equal to minus 2R. 2R transmit and receive 2R. And here the ratio of the pulse 2 pi divided by lambda. It is the ratio of the phase. Yeah? Let's consider how to, if you can derive this R, you can find the information on the phase. Yeah? Okay? Yeah? And let's consider R. If we just consider this one, this triangular relation, the Pythagoras, yeah? You can find that R, this one, equal to RO square plus X. Yeah? This one X square, and just the roots. But please don't forget, we must consider the Earth rotation velocity. Earth, this Earth velocity is A and T. If you want to observe the Venus, you must also consider the velocity of the Venus. But Mars also, just put the Mars rotation velocity. Yeah. Okay, then you can find this one. It is look simple, but actually complicated. Yeah. If you want to make the calculation, so you need the approximation. Yeah. Then you can make the approximation RO plus this one and just remove this one, and then you can find R. Yeah. R. Then this R you insert to R here, and you can get this. The phase. Yeah. The phase. Okay. Until here, how to derive the phase. Okay. Depend on the effect of the Earth rotation. Yes, Earth rotation. Then, okay, please remember, if you can derive the phase to the time, you can get what? Frequency. Yeah, frequency. Yeah. So you can get the frequency. Yeah. This frequency is the azimuth frequency. Yeah. Okay, then just derive this one to the time and you can get this one. Yeah. And then if you got the frequency, then insert to this one. This I explained to you. That's about the wave propagation. Yeah. Then just insert to F here and you can get this one. But in this case is later you must consider the constant. Constant is depend on the power of your radar, yeah, at the distance. Many, yeah. Then you can get the reference function of your radar. It's like this. Yeah. It is the reference function in azimuth compression, in azimuth direction. Yeah. Okay, and I'm already explained you the range in range compression. You also we also get this reference function in range compression and at azimuth compression. But if you compare, almost same, yeah, almost same, yeah? Or similar, yeah? Similar, and just the constant. Okay. Then and if you process in range compression and azimuth compression almost. You can use just one function. Then with the subroutine and send the component and use this send just this component and you can calculate the same subroutine. Okay, and next, if we you tired? No?
No problem.
No problem?
No problem.
Okay, and then azimuth compression. Yeah, and azimuth compression is because the effect of the Earth rotation and the effect of the moving of your spaceborne on the aircraft. So you will find some effect we call as the range migration. And the range migration is why I explained to you that the response, the response from the peak, from our spacecraft. So look like this.
Range
Block. This block is not just from the chart pulse, but also from the effect of the position of your aircraft to the object and the rotation of the Earth. Yeah. The ideal one, you must stop the rotation of this Earth, but it is impossible. Almost impossible. Okay? So in this case, we must consider this effect, and you can make the correction, and you can find better image. Okay. The range migration itself is composed by the range walk and range curvature. This makes effect to be range migration. Yeah? You know, range walk, or we also call it the range skew. Yeah? It is because the effect of the Earth rotation. Yeah? Okay? The Earth rotation is to be like this one. Yeah? Actually, we want to observe the object is, must strike, but actually we will find the object is moving. We observe, then we observe like this one, it's Earth is rotate like this one. Yeah? So when we moving like this one, our object also move. Yeah? Move. Yeah? It is happen when the object and the spacecraft is very far. Yeah? But if too close, like UAV, is maybe you can neglect this effect. And then range curvature. Range curvature is because the effect between the platform and the target, the distance of the platform and the target. And remote is to be like this. Okay, I want to talk one by one. Okay, this is the time. Yeah, the time. Actually, when our satellite moving, at the time one position here, but when satellite moving is position here. This is when we see from our if we in the spacecraft, if we see the object, why this object is moving itself, like this one, we cannot stop, because I think when we write the International Space space craft, I think we will find something is is moving and we also moving, like this one. This effect. This is the Earth rotation, and here the effect of the object moving, and we move. And you can find in the image it look like this one. And then it is the range curvature, because the distance between the spacecraft to the object. Yeah? When we want to observe this object, because the beam width of our antenna is large. Yeah? Even we are here, but we already catch the response from this point. Yeah? Then we will save to here. Yeah? Then we move here, the response from this point we save in our image, save here. Yeah? Then like this one. And if you find, it is the closer one and you save here, you can find actually the response, the real response is this one. But you cannot remove this one. Yeah? Because in this response is mixed with another response. Yeah? Yeah? So you cannot remove directly. So you need to cover this area to remove this position. Yeah? To generate this pixel. Yeah? Okay. You'll find in the image is the response like this. Yeah? Okay. How to correct this range swap? Yeah? This one first to correct this range swap. It is until here is almost same. Yeah? The R, yeah? R is equal to this one, and we make the approximation to be here, and just derive this R, yeah, to be like this one, and if the T0, yes, if this T0, yeah, include here, and this derivation is 0. It means, it's no change, yeah, no change. No change, or no change, yeah. I mean the change of we moving, but this location change is 0. Yeah. In location change 0, you can define this position as the Doppler center frequency, the real frequency, yeah, the real frequency. Even you send 1.27 gigahertz, it is the central frequency, but this one is,
due to
it is the real, it's not the real frequency. The real frequency is after this derivation, after the effect, we consider the effect of the Doppler frequency. Okay, and okay, yeah. Then here, it is another technique. How to derive the Doppler center frequency. Yeah? If you buy the data, it is the raw data. Yeah? First is you make the range compression. Yeah? Range compression. Then select. You can select this area or this area or this area. It's up to you. But maybe better is you select the center. Yeah? On the center of your data. Yeah? Then make the this direction. You select 2 power by n is because we need to make the FFT. Yeah? FFT. Then you make the FFT here. Then you make the average. Yeah? Averaging. Yeah? This averaging to this direction, and you can find if averaging 2n pixel on the Fourier spectrum, then extract frequency, and when the spectrum is peak, the peak. Yeah? Last time is when when we move, yeah, here is the frequency will increase then drop. Yeah? When just increase and here the peak. When the frequency is to be peak, yeah, this one is the real frequency. Real Doppler frequency. So you can just resampling from your image. So the real Doppler frequency in your image is how many gigahertz? Yeah, it depends on this. Then, if you already get the frequency, Doppler frequency, then you use this frequency for the FFT result. then you just make the calculation and you can get the real value of each pixel. Each pixel. Okay, it is one of another. Then here's for the range curvature correction. Yeah, to correct this range, this one. Yeah, range curvature. Because you know this effect, you need to move this object to here, to make a straight line. Then okay, until here is almost same, almost same. Then you calculate the FDD twice. When the acceleration of your satellite is to be like this. This is double feet. Or here R twice. Twice we make the derivation or differentiation. Then you can find here and the RT is equal to FDD T tau. R tau. R tau. You want to make this position of this position is to be here, and make straight. Okay, and okay, you can imagine. Actually, if you make the straight, after you make straight, then you make the straight line. Because this from this response. In the Z1 is 13.4 kilometer. First, you make the range. You can see.
Okay. Thank you.
Okay. I will. Okay. For example, stop. Sorry. Okay. Yes. This response. So for example, this response is you need from this response you must change to be line, this line, but this line is still bending like this one. You must process to be one line, to be this line before you make the azimuth compression. First, your line is must straight. So this RT, this change here. RT is this one. This RT. You need to make the change. Make a straight. After you make straight, this line, then you compress in azimuth direction and to be just one. Just one line.
You are using interpolation to correct the
interpolation. Yes, because actually we also need to use some filter. Some filtering. Filtering is to first. Sometimes we cannot process directly. We need to reduce the noise. After reduce the noise, and you can find, here actually here is the intensity is high, high. Then you maybe here.
Yeah.
Then
Some paper.
you need to be like that.
Smoothen first. Yeah.
Smoothen
Then only
first, then
interpolation.
fine, yeah. Because if you include this without the filtering, I think your face information will affected by the noise. And if we use we use this data for insight, will drop the quality of our insight. Okay. Yes. Okay. Okay, this is the final one. It's not so difficult. Yes. This is multi-loop. Yeah. Multi-loop is for example, the multi-loop with four. It means you merge 4 pixels to be one. It is the easy one. Yeah. Then averaging to reduce the noise. Yeah. Reduce the noise. Multi-loop 3 is mean okay. 3 pixels to be one. Yeah. Multi-loop 4 pixels to be one. Yeah. Just averaging. Because sometimes the next pixel is affected by the double bounce, okay, or another what is we call it the speckle noise, but actually it's not noise. Yeah. But the wave, yeah, if one wave and another wave, will the amplitude is overlap, is to be high. Because speckle, yeah, speckle, it's not noise. Okay, yes, finished. I want to continue to the characteristic. Yeah? Okay, maybe 30 minutes. Okay. Actually, I also have the mode. Yeah? I'm skip. We don't have that. But I just want to show you. We have the street map. Yeah? It is the common one. Yeah? You can check out before the characteristic. Street map mode. Yeah? It is, for example, just one also street map with the here. You can find?
Yes.
Street map with 17.9 kilometers. Yeah? To generate just one. And the speed of our spacecraft with 7.6 kilometers per second. It's very fast. Yeah? And then, okay, the beamwidth here is just 1 degree. Yeah? To generate here 6 meters. 6 meters, half of our antenna. Yeah? It is the strip mode of the jet one. And then, okay, the street map, but you must consider this street map. The footprint, even in the same footprint, but the equal distance, some part is different. Yeah? How to make the focusing, it is also one of the topics. And here, this is in the equal distance, but here is a different. And the equal Doppler line, it means the Doppler line here is, it is same. The frequency is same, but here is different. Okay? You must consider, even in the same footprint, but the Doppler frequency is different. Okay? Okay? So, I think how to extract just the response from the same Doppler frequency. It is also one of the topics. Yeah. Okay. Street map mode is, I think, many platform, including our satellite and our UAV. And next is the script mode. Script mode is, we move like this one, but our antenna is moving like this one. Yeah. Yeah. So we can observe one point twice. Yeah. This direction, forward and backward. Yeah. So, but you know, the shape here is a diamond. It's not square. But the benefit, you can make the DM clearly compared just one time. And resolution is much better compared to the strip mode. But here the spotlight. Spotlight is you know, moving, but you know, just observe. Yeah, the same area with more longer. Yeah. And you can increase. And if you can observe more longer, and you can get your resolution. Here's the, I think the maybe slightly is almost equal your lambda. Yeah. If L-band, for example, you use this one, the spotlight, you can derive L-band is 23 centimeter. Yeah. But you must, you know, observe at the same time it's very long. Yeah. Sometimes. And how to make the system is also one of the and it is in first mode. Your radar is fixed and object is moving. Yeah. It looks like if you want to observe the ship, yeah, ship, yeah. Like in around the Malacca Strait, there's many periods. Yeah. In the night time, you can put your radar and you know, you can observe the ship. And you can make the detection, the type of the ship, yeah, from the response of from the radar. Scansar is, you know, yes, observe here, then here, then back here, like this. If we want to observe, it's very large, yeah, large area. We have the Scansar radar. I think not many. Aerospasar, also the NPSAT, they use the Scansar. And then burst mode SAR. It is for the deep space mission, yeah? Because the energy is not so much. Yeah? So they observe here, then you know, take a rest, observe again, take a rest, observe again, take a rest. Yeah? You know, because we want to save the energy. Yeah? Energy. It is for the Magellan. Yeah? Like I'm already show you the image of the, you know, the Venus. Yeah? Let's use this mode. It's very nice. Yeah? But the resolution, of course, is wrong. It's not so good. Yeah? Okay. And wave mode. Wave mode, if you want to observe the ocean, you don't need to observe whole of the ocean. You know, consume power much. So you just resampling. You know? This one. Yeah. Partly. And wave. Okay. This is better. Then let's consider the characteristics. If we want to observe soil, rock, or small vegetation, almost same, the characteristic. Yeah, L-band is can, you know, penetrate. Then, but here the scattering, yeah, because penetrate more, yeah, but the response is low. Yeah? Yes, is low. Yeah? And C-band and H-band. X-band is higher because it's scattering very easy. Yeah. Yeah. And here's almost same. Yeah. LCX. And it is the effect of the incident angle. if the incident angle is large, yeah, you can find your object is clear. Yeah. But here, the crater is almost, what is destroyed. Yeah. But here is clear. Yeah. Because the incident angle is, it is more lower. Why lower? Because they want to make the power safe. Yeah. Power safe to save the power. As low is very close. You don't need a very strong power. Here is the S1 and Z1 with the wavelength. Yeah? If the wavelength is larger, you can find more easier. You can discriminate every object. You can find here the Japanese Army training test area, and here the forest area and snow area. But here you cannot discriminate, because the wavelength is small. It's easier, scattering. The scattering from the forest and from the grass is almost same. Almost same. You can remember what I'm explaining in the smooth, slightly rough, and rough. Yeah? It is almost same. Almost same. And it is the bow tie effect. When it is a large agriculture or farmer area. Yeah? When they open the area, they use the tractor. Yeah? Tractor then open the soil and make the soil like this one. Yeah? If this line is almost quarter lambda, quarter lambda, and the scattering. If perpendicular, very strong. But if the wave it come from here and will go there, it's not come back. Parallel. It is same. Here strong. It means perpendicular. But here black. It means parallel in the wave. You can predict. Oh, so the satellite is moving from which direction to which direction? The satellite. Our radar is side looking. The radar is this one. So, but the satellite is like this one. So you can remember. You can read from your radar image. Oh, my satellite is moving from which direction to which direction. You can predict. And what phenomena? Okay. And next is almost same. Now is this radar. This radar image. How about the response from the spoiled water spoiled agriculture? When they manage this agriculture area, like this one, then they use the maybe tractor like this. If the flight like this one, and radar here perpendicular. If here perpendicular, well strong. But here is parallel. Parallel. So here is black. Black, but here is very strong. And you can find the next response like this. Here is perpendicular, but here is the parallel. Okay, you can begin. Then next, in the image, you can find actually this bridge is just one, one wire bridge, but you can find is two, or maybe here the effect is to be three, three wire, Why? Because it is the satellite is okay. the satellite moving from which direction to which direction? You can see, you know, this project. Here shadow, and here the yeah, maybe like this one.
For side.
We try it here and here the foreshortening. Then you can consider later. Yeah? Then oh, this one is the first scattering is this one. Okay? This one. Transmit indirect scattering. Then another one is the wave is scattered by the sea surface, scattering by the wire and go back. So this line, okay? This line. So you can calculate this line. So from this line you can consider the head of the bridge. For example, if you never go to the Pyongyang, yeah, maybe you can estimate the head of the bridge. Yeah? If you cannot go to somewhere or Iraq, yeah. So if you afraid to go and but you can analyze, yeah, from the sun. Okay. Then okay, it is how to calibrate by using the corner reflection. If you buy the data, you can find DN is the digital number. You can just enter the digital number and here the constant, the constant ratio. Yeah. How to derive the constant ratio? We can derive by using the corner reflector. It is our corner reflector. Yes, it is very big. I think the weight is more than 100 kilograms. It's very big. Okay, I don't want to explain this one. I think I didn't put this one. It is hard to calculate. Because I said, you put here?
The sigma naught, the earliest one. So we have to measure ourselves, or they will provide by the, we have to get the value of ourselves through the experiment.
Right, yeah. This one, CF? Yeah. Which one?
Sigma naught.
Sigma naught, yeah. The back scattering coefficient.
We have to measure from the experiment or the data, they will be provided, or we have to measure ourselves.
Okay, actually, if you buy from the space agency,
yeah,
you can find the standard one. It's very easy. And you can find, if you buy, for example, just one, the data that recorded in 1996, you will find, or CF in 1996 is how many dB? Okay. They already defined. But if you have your own satellite, so you must make a calibration by using this one, this instrument, because after you launch, you know, as I think your satellite will degradation, including the performance on the function or the transmitter itself, yeah, all is degraded. Yeah. But if you want to compare the data get in 1992 and 1996, I think actually the performance of your satellite is different, but how to compare this image? Yeah? So we need a standard, standard before we compare. Yeah? So this standard is used. First is calculate the backscattering coefficient or sigma.